Hi everybody, welcome back to Hey Chem. We're here with episode 5b, all about combustions. Combustions are a super fun topic for a lot of people, just because you get to talk about fire, which is pretty cool, at least in my opinion. So we are going to jump right on in. Alrighty, just for some definitions and some background, a combustion reaction really can be defined as a reaction with O2 as a gas in excess plus some sort of compound that yields CO2 gas and water as a gas. For the sake of this video, we're going to just assume that X is an organic compound. That's usually a safe way to go with these intro classes, and that's okay. So we're just going to look mainly at compounds that involve C, H, and O, carbon, hydrogen, and oxygen. So one of the really important things that instructors express is that O2 is always in excess for these reactions. It needs to be, otherwise the reaction won't take place. So just keep that in mind. I always write a little excess with my O2 when I'm doing a combustion reaction. And these reactions always yield CO2 and H2O in some form. If you're working with something that might not combust easily, like a metal, you might add it, alongside, something that might not spontaneously form with CO2 or H2O. But again, for the most part, we're just going to look at CHO compounds for this episode. Your instructor might, throw in nitrogen, sulfur, phosphorus. That's okay. Those are all organic compounds. So, but I didn't want to throw anyone off. The cool thing about combustion reactions is that we can calculate an empirical formula from them. An empirical formula is kind of like not working backwards, but it's calculating ratios. CXHY to OZ is kind of what our model organic is going to look like, and given certain information we can calculate X, Y, and Z from these scenarios. So I have an example problem. It's pretty lengthy, so just hang with me on this. But we're going to go through calculating an empirical formula, and I'm going to show you kind of what the steps to do that, and at the end we'll calculate some weight percents. So our given is O2 gas plus some sort of identity compound yields H2O gas and CO2 gas, and we're given amounts we're given masses 1.2 grams of X and O2 excess yield 1.13 grams of H2O gas and 2.086 grams of CO2 gas. And our question is, what's the empirical formula for X? So we're given that X equals 1.2 grams, H2O equals 1.3 grams, and CO2 is 2.06. We know our O2 is in excess, and our goal organic molecule is a CHO compound. So we could kind of write it like this, kind of like I wrote earlier, CXHYOZ, etc. Hopefully a lot of this is just to help visualize the problem. This sort of problem is difficult to teach via person to camera, so just hang with me here on this. So our first goal, or our first step for finding the empirical formula for X, is to find the grams of convert the grams of CO2 and H2O to moles CO2 H2O, and from that we want to calculate the moles of carbon and hydrogen released in these products, because that will give us the moles of carbon and hydrogen or the amount of carbon and hydrogen in the unknown organic molecule. So in this equation we calculated just up to grams of carbon, so that's skipping a few steps. Not skipping, but it covers a lot of steps in here. So we calculated the moles of CO2 here, given, and then from the moles of CO2, I calculated the moles of carbon in that, the moles of carbon produced. And then for moles of carbon, I calculate grams of carbon produced because, you know, law of conservation of mass, you're not going to lose that carbon. It's going to come up in your CO2. So that's kind of a nifty nuance to build this on. It's going to be the same case for the hydrogen as well. 1.13 grams hydrogen is converted to moles, oh, not hydrogen, sorry, water. 1.13 grams water is converted to moles water. And then from there, we're calculating moles of hydrogen, and notice the 2 mole H because of that awesome molar ratio. And then from there, we calculate grams of carbon produced. So far, what we've calculated is the grams of carbon and hydrogen produced from this equation. So grams of this and grams of that. Now we need to find the grams of oxygen released from X, and the way that we can do that is simply by subtraction. We have our grams of carbon and hydrogen, and we have our total grams of X, so we can just subtract what we know and find grams of oxygen. Hopefully that's pretty straightforward. Now comes the awesome part. Now we get to do molar ratios. And this is just a little picture to kind of help visualize what we're doing. We're taking all the pieces of the pie, and now we're putting them together. We're calculating them together. So the first part of that is we're going to calculate the moles of carbon, hydrogen, and oxygen released in our end products. We can do that because we have the grams carbon, hydrogen, and oxygen used in our CHO molecule compound. Hopefully this is making sense, and we're going good. So we'll take those values of the 0.5618 and the 0.16126 and the 0.5122. Calculate moles of carbon or moles of hydrogen on that, and moles of oxygen. The main thing now is to identify which one has the smallest molar amount. This will vary from problem to problem. In this case, that happens to be moles oxygen, so we'll divide through by moles oxygen. This graphic with this pizza, I'm calling it a pizza because pizza, is kind of to show you what we're doing in a more visual context. We're taking these ratios or these amounts of moles carbon, moles hydrogen, moles oxygen, and we're dividing them through by the smallest one, and then we're getting ratios from that. So if we took our 3/8 and divided our 3/8 by our 1/8, we get 3. So we know that if this were, X and this were Y, it'd be 3X to every Y, so to speak. Hopefully that kind of helps. I just want an excuse to draw a pizza. Anyway, so here's all our moles, and we know that moles oxygen is the smallest, so we are going to divide through by moles oxygen. Don't do what I did initially and divided the moles oxygen by your other amounts, because that's not going to get you the answer. I can guarantee that. So divide your moles carbon by your moles oxygen, your moles hydrogen by your moles oxygen, and you get these ratios of moles carbon and moles hydrogen to oxygen. You don't necessarily have to include this on your homework or in your work, but I put it here just to show that when you divide your moles oxygen through, you get a 1-to-1 ratio. So that kind of makes sense. It'd be a 1-to-1. And then you can you write everything out in your first equation, your first compound. In this case, our carbon is 1.5, and unless stated otherwise, you gotta convert your molar ratios to whole numbers. So we're just gonna multiply by 2, and we get C3H8O2 as our final compound. Whew, that was a lot of work. Good job, everybody. Way to hang in there. One last note, some professors might want you to calculate weight percent of anything in this, or you know, limiting reactant, percent yield, etc., which is why I did those ones before I came to this equation. And now you are all set, because I have videos on how to do that. If you have any questions about this, please let me know. Please drop in a comment, or you can email us. I made kind of a spreadsheet for the ideas of how to solve this problem. You can pause and take a look here. Hopefully it makes sense. And I mean pizza, come on. Anyway, so kind of to the cool part of the episode where I get to light something on fire just because it's a combustion reaction and I can. So this is a lighter, right? Just a regular Bic lighter, not a sponsor. I don't have any sponsors. Not a plug, because, well, I gotta get viewers first. What? No, not salty, not bitter at all. Okay, so cool stuff like this, lighters, butane, torches, lighter fluids are gonna house something like a petrol or petroleum or an alkane. A lot of lighters you hear about, you can see, you can find, have butane in them. Butane torches, etc., C4H10, and so you can kind of see with an X plus O2 yields CO2 plus H2O, you know, that C4H10, excuse me, C4H10, you know, manifests here and here, so to speak, and it doesn't always need an oxygen molecule because there will always be excess O2. So, a real life demonstration, if we just light this on fire, the carbon in the paper plus the carbon in the lighter fluid are combining with the oxygen in the air, creating light, heat, CO2, and H2O gas. Woo! It's probably the most fun I've had on HeyChem. And the most satisfying thing I've burned in a long time. Don't tell the police! Anyway. If y'all have any questions, comments, concerns, or feedback, please drop us a line either here at YouTube or at heychem.com. Love to hear from you guys, and I'd love to talk chemistry. Until the next video, as always, be safe, have fun, and eat lots of pizza. Thanks, guys.